a good problem. So let me pose the third problem as a homework problem for you to solve that by work and energy principle, and then I will complete today's class. So that problem number 3 is again here it is a conservative system you can consider. You have arrangement of mechanical system wherein you have first one bar, vertical bar, which is fixed here. So in this is a smooth bar, in that you have a collar which can slide in this bar. It's a smooth bar and it can slide. There is no friction that you are going to consider in this case. And this collar has been having its motion controlled. See, I want to raise this collar. The collar will have some weight, so that is why it is now here. And if I have to raise the weight against weight, I have to pull this up. And I have to have a controlled motion, so I will have an element called a spring here attached with this. And that is tied here. The length of the free spring, if you look at this, that's 0.5 meter. Right? So let me read the statement of the problem. A 25 per kg collar, a steel collar, is being raised from rest at position 1. So position 1 is here. This is position 1. It's being raised. It is in a rest condition by a 400 Newton force. So where is this 400 Newton force? That 400 Newton force is applied onto the collar, which is inclined 70 degrees to horizontal. 70 degrees to horizontal. There's a 400 Newton force here as well. Newton force applied as shown. Applied as shown. The collar is guided on a smooth rod and spring whose free length is 0.3 meter. So the free length of the spring. So the spring is attached here. The free length of spring equals 0.3 meters. So what do you mean by that? When now the spring is shown in a horizontal position, that means it's 0.5 distance. Means the spring is a stretched spring. Already there is a stretch in the spring. So that will pull this collar here. And since the collar is of smooth contact surface, that won't have any resistance during the motion, but it will have a normal acting on this. Right? So that is what. So this orientation shows 0.5 meter. But the free length of the spring given in the statement of the problem is 0.3 meters. There's an initial deformation of the spring. So that is required. So already it is stretched me, there is some energy that's stored in this spring. And then further it is moving up. Then the spring also getting further stretched. So that will have again energy getting added to the spring. So this is position 1 and this is position 2. Where you are taking this collar by this force, and this is of height 0.8 meters, 0.8 meters. It has been raised. So now what is its final speed of the collar as it reaches position 2? Find V2 of collar as it reaches position 2. That's the question. By work and energy principle, you can do it. So that is what is going to be like this. The spring will be stretched from here, and the collar would have come here. That's position 2. Determine this. So from the top of the collar, this distance, top distance is 0.8 meter, right? So solve this problem as homework problem, and you of course require the spring constant K here. That's given by 300 Newton per meter. So where it's called the spring stiffness, linear stiffness of the spring. So force required to create unit deformation is what is K. So K into deformation will be the spring force. So you will have here, as already it is stretched, you will have a spring force here. But that is at right angle to the bar. So here it may not participate in the work equation, but as it goes, there will be an inclination that will come. But accounting that become tedious. That's why here an advantage of applying work and energy principle. So at this point, what is the kinetic energy of this? And from work 1 to 2, what is that work done? And at point 2, what is the kinetic energy? As it is said, kinetic energy starts on rest condition. So KE1. So of my KE1 plus work done from 1 to 2 is equal to KE2. This is 0 now. So work done from 1 to 2 I have to find. So work done by this 400 Newton force, which is inclined, will have its component along the bar and perpendicular to bar. Along the bar will be contributing for work for displacement of 0.8 meter. And the weight is acting down, so work against weight, negative work. And the spring work from position 1 to 2 is to be calculated. So that would automatically come if we are considering the spring work done from spring. That I just write the formula, it's simple. It will be half K x1 squared minus half K x2 squared. So whatever the energy that is getting stored, expended is what is for the work done by the spring. The spring is not doing work. As it has been stretched, work is done on the spring. So that would come automatically if I take initial deformation of the spring at position 1 and final deformation of the spring at position 2, that's x1 and x2 respectively, and K values are given. So this difference is what is work done that comes from the spring. And work done by this force component into displacement and weight into displacement. So this all will be contributing for U12. And that's what is equal to half M V2 square. So I will be able to find V2. So work and energy principle is easier here instead of going for Newton's law to apply, right? So that's what is that. I will stop at this point, and the next class we will solve some problems which would relate maybe again kinetics of impact collision problems we'll do, right? Yeah.
So if
you have any doubts we can ask.
Spring force is there, then the system is conservative or non-conservative?
Conservative system, because spring is a conservative system. There is no loss of energy in a spring, right? It is not a damper. So there are materials like rubber tire, no, it is viscoelastic material. So you have to model that as a mathematical model. You'll use spring and damper something. So damper is something which is representing energy dissipating setup, whereas spring is energy storing or energy expanding system, which is conservative system, right? So here change in potential energy is what is this. And since it is a smooth surface, the work done, whatever you get, it is same as that of change in potential energy in the system. In this problem, supposing this bar is given, it's a rough surface and mu value is given, then what is that you have to do? In addition to this force, there is a resistance acting down. So you have to consider that. So there is a kinetic friction force that also will be coming into the system. At that time, it is not a conservative system. Yeah, but you will apply anyhow this equation only. So you will have addition to three terms, one by the weight component, another weight component, one by this component of the force. Other term is this. You will have an additional term which would be mu k times 400 sine 70 into 0.8. That term will not be appearing as we are given. This is a smooth rod. That's the difference, right? Is it clear?
Yes, sir.
Yeah.
So you have taken the attendance, right?
Yeah, yeah. I have to take it before closing. Otherwise, I have to give attendance to everyone. Yeah, I'll download the attendance. I stop sharing. Stop recording.